If we look at our lesson for today, it says that we are going to do practice problems up here, and we're going to do a mini steel lab in the back. Okay? So before we do that, I'm going to go over the mini steel lab for those of you that are going to be in the lab. The people that are up here, ma'am, are going to be doing word problems with me. Okay? Look over the lab, please. Okay. The way that we're doing lab today, remember, the people that went first last week go second this week. We're going to flip back and forth. That's how we're doing it. So let's look over the lab to see what we need. Okay. Those of you at home, you will not be responsible for the lab, but I am going to go over it with everyone here and everyone at home just so that you can see it. So if you go into the agenda for today on week 3, if you go into Monday, you're going to see the attachment of the lab. I'm not. Okay. So it says here, steel ball race. Said, read the procedures and safety information to complete the lab. Assemble an inclined plane with a piece of U-channel with 2 meter sticks taped together. Measure 40 centimeters from the top of the ramp and place a mark there. Place another mark at 80 centimeters at the top. Predict whether the steel ball will get closer or further away as they roll down the ramp. And at the same time, release one steel ball from the top of the ramp, the other steel ball from the 40 centimeter mark. Record your observations. Next, release one steel ball from the top of the ramp. As soon as it reaches 40 centimeters, release the second ball and explain your observations. Did the steel ball have the same velocity as it rolled down the ramp? Explain. Flip over, please. Do you have the same acceleration? Explain. The situation in step 6 different from step 5. Okay. So the people that were in the lab first last week are not going, but the rest of you are. So go ahead and get up and go to your lab station. What do you need? You need this piece of paper. You need your pencil. And I think that's it. So come on and go to the lab. You didn't bring it in. Come on. They went to first last week. What? Don't sit up here. Where you at, honey? So right now you have the ramp. Okay? Your floors are here. Here's the steel ball that you will need, the 2 of them. Okay? And then also you'll need timers, which I'll bring in the back for you. I'm going to give you some tape to take your measurements. Go ahead and get started. The people that are front, go ahead and go. Let's go to our page. And the page that we're going to go to It is page number 65, please. Page 65. So, first of all, what we want to talk about is what we've wrote down so far. So what we wrote down so far was the particle model, what a particle model looked like, right? When we're talking about vectors, we talked about direction and magnitude. We talked about when you have two vectors that are going in the same direction, you add them. If your vectors are going in two opposite directions, your displacement is the difference between those two. And the last thing we saw so far is rise over run. We wasn't able to finish the reading assignment. What other thing do you think would be important for us to put on our blue side of our board that we might need today? The slope formula. Okay? So if we're looking for, we're going to look for average velocity. Average acceleration. Sorry, guys. Okay. So average acceleration is the A with the line across it, right? If you remember, I'm on this page. I'm doing this one first. That's okay. I'll go back to that one. No, leave it there.
I just did report.
Oh, I'm so sorry. So if you remember, the line over the A means average, right? And we're using A today. We did average velocity before, right? Now we're going to do average acceleration. So when we're doing average acceleration, it says change in velocity over change in time, right? Now, when you see that triangle, what does that mean? We have a final, we have an initial, right? That's what it's telling me, isn't it? So we're going to have velocity final minus velocity initial over, there's the change again. So we're going to do time final minus time initial. Everybody so far know what we're doing. You know what the symbols mean and what we're talking about. Okay. Is there anything else that we need to have up here? We already got our rise over run right here, right? Okay. Anything else? All right, so let's look at the sample problem. So on the sample problem, what are we trying to prove here? Yeah, you need to pop some things underneath it. You use the books too if you need to. Just one side because you want it to be a ramp. Y'all are reading over the sample problem.
Weird.
I know it's a little different having lunch off that early, huh? Okay. So here it says velocity and acceleration. How do you describe their sprinter's velocity and acceleration shown as a graph? So the first thing it's telling us from the graph, note the magnitude of the sprinter's velocity starting at 0, increases rapidly for a few minutes, and then reaching 10 seconds, remaining constant. So we're looking at the graph that we've got, right? So can we choose any point on the graph, or are we having to choose a certain thing? It says draw a tangent to the curve, 2 points. Choose t to 1 second and t to 5 seconds and show the magnitude. Okay. So what they're doing is they're looking on the graph, right, guys? They're trying to find these two spots Remember, time is on the bottom, velocity is on the side, isn't it? Do you see where they get 10 minus 6? Do you see where you got 10 minus 6? Okay, that is the rise. The run is 2.4 minus 1. Do you see where they got that from? So if you go to 10 minutes and go up, and you go across, what do you see?
The lines intersect.
Yep. So let's take our calculator. Let's see if we can do this math. Okay. Alpha y enter, right, guys, to get our fraction. So we're going to do 10 minus 6. Yes, ma'am. And then you're going to, that gives you your fraction. Do you have your fraction? Okay. Then you're going to do 10 minus 6. Do your arrow down to get to the bottom. 2.4 minus 1. And hit enter. Did everybody get 2.857? Do you understand why they rounded it up to 2.9? Sig fig rule, right? So then the next thing we're going to do is it says solve the magnitude of instantaneous acceleration at 5 seconds. So let's go to 5. Do you see where they get the 10.03 and the 10 at?
Let me go back. I don't know where they got the 2.4 seconds runs to 1 second.
Okay. So we're looking at T at 1 second and T at 5 seconds. Are you there? Okay. If you go up, what do you have?
Oh, what?
Go up to where the line is, where the blue line is.
I don't see the blue line.
Okay. So go to 10 and go to 6 and go across.
All right.
And if you go down to the time, it should be 2.4. I'll show you. I'm sorry.
Yeah, it's right here. And then if you go down, it will be 2.4. But where'd they get the 1 from?
That's where it starts from, which is right here at 1. Right there.
Where's the 2.4? And
2.4 is right here. That's where that line is and that line is. We're going down both of those. Okay, are you good? Okay. This graph is not the best. Do you see it now? It's difficult because the graph is horrible. Okay, so the next one we're looking for the magnitude of instantaneous acceleration at 5 seconds. So if you go to 5 seconds and you go up, 10.3 minus 10. Do you see where that's from? How about 10 minus 0? Because we started at 0, we ended at 10. So let's go ahead and do that math. Ready? Alpha y enter. We're going to do 10.3 minus 10.0. Arrow down. 10.0 minus 0. And hit enter. I got 0.03. Is that what y'all got? We're all good so far. Let's flip over the page. Now we're going to do question number 1. Question number 1 says the velocity time graph on figure 8. Do we see that one? I'm going to do my best to draw it on the board, so just bear with me. So here we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Right, guys? And then our velocity really don't have anything even written, do we?
No.
We have it here, and where does it goes across till what? 2? And then it goes down 3. And then it goes across to 5. Okay. It goes down to 6. Down at the bottom 7. And then it goes up to when?
About 8.
About 8, and then it goes across. We're all good so far. Okay? It says, the velocity time graph on figure 8 describes Stephen's motion as he walks along the midway of the state fair. Sketch the corresponding motion diagram, including velocity vectors in your diagram. Okay? So how are we going to do that?
Corresponding. So they just put in you don't.
We're doing dots, right? And lines, right? Does everybody agree? Okay? He's at a constant one, right?
Yep.
Okay, so they have to agree with each other, right? Okay, what happens to his velocity? Decreases. So it's got to get
Small.
smaller. Okay, and then what happens?
Stay the same.
Maintains the same speed.
Okay, so same length, right? Then what happens?
It's even smaller.
Okay, maybe I shouldn't have done it so small. Okay, then what happens?
Maintain.
And then he maintains that one. Okay, and then what happens? Okay, I can do this one. And then what happens?
Maintains that.
Everybody understand?
And so if you stay the same, it gets smaller.
If it stays the same, you want it to be the same size.
That's why I got small is because it's basically touching that x-axis.
Yeah, it's all the way down to here. So that is the smallest. You could do dots. Dot would even be better than that little arrow. See, I went there and tried to go smaller, and then I stayed the dots, and then I went bigger. And then I try to do the same. Everybody good with the first one? That one's pretty easy, right? Okay. So number 2 says, using a VT graph of a toy train in figure 9 to answer these questions. So let's see if we can do that one. So on that one, we have velocity over here. We have time down here. We're in increments of 10s, right? All right. We are in increments of 2. All right. Where do we start at?
0.
0. Where do we go to?
And then,
Up to 10.
5 seconds, but 10.
5 seconds, 10. Okay, I'm there.
And then you maintain that for 15 seconds.
Till 15 seconds. All right, I got that.
And then you go down to 4 meters per second, velocity to 20 seconds.
Okay, got it.
And then you slowly lose velocity to 40 seconds.
And that's about it, right?
Yeah.
And it's down at 40, right?
Yep.
So I think I got my graph right. So the question is, when is the train speed constant? This one right here, right? That is his constant speed. Everybody agree? Okay. Says, during what time interval is the train's acceleration positive? From here to here, right?
Yeah.
That's positive, isn't it?
Yeah.
Okay. Where is the train's acceleration the most negative?
Or no, it would be between
Right here, right?
yeah.
And the reason we know it's the most negative is because it's straight down. It's not a curve. We're getting this. We're understanding how to read graphs. We're doing great. All right, is everybody ready for 3? Refer to figure 9 to find average velocity of the train during the following times. 0 to 5 seconds. So we're doing 0 to 5 seconds. Okay? So are we using this formula?
You're just using the top portion.
Are we trying to find, what are we trying to find?
Oh, it is? Yeah. Yeah, it is that one.
Right? Okay. So what is our time final? 5 seconds, right?
Yeah.
What's our initial time?
0.
0 seconds. All right? So we got to take that, but we got to divide that by what? Our positions, right?
And velocity minus 0.
10 minus 0. All right, let's put that in our calculator. So we're going to do alpha y enter again. We're going to 10 minus 0 over 5 minus 0. And I think I already know what the answer is, but I'm going to do it anyway. And that's 2 meters per second, right? Everybody good so far? Okay, so let's see the next time that it's looking for. 15 and 20. Okay, so what is my final time? So I'm doing 20 seconds minus what is my initial time?
Or 15.
15 seconds. And then what's my position at 20? 4 meters minus
10 meters per second.
10. Okay, let's do our math. So that is alpha y enter. 4 subtract 10 over 20 subtract 15. What do we get?
-675.
Yeah, you got -6/5. So let's do this. Ready? -6. We're making it linear. Remember? -6 divide 5. Enter. -1.2. And that is our answer. Are you feeling pretty confident? Okay. 0 to 40. All right. I'm going to let you do this one on your own. Go ahead. We're not going to do the challenge with, but do number 3. Doing good? Okay, so what do y'all do? Distance divided by time.
Maybe they meant from 20 seconds.
If you don't have enough. So now what I want you to do is I want you to the better back. Right here's the bottom. I want you to make me a database. Positions and time. Okay? And you've got all one and all two. Check the time. All right, what did we get, guys?
0.
We got 0. Wow, Miss Sloan chose the right one. Okay, so let's look at the next example. Are y'all ready? Okay. Huh? No, everybody got 0. I think we're all good. I trust you. Maybe I shouldn't. Are you saying I shouldn't trust you?
I think it's a weird problem.
Oh, okay.
Because
So I will, so in other words, you want me to check it. All right, there it goes. That's what I need. Sorry, guys, I got to set this timer. Or I'm going to have y'all forever, and y'all know that. Okay, so what is the positions we're trying to find? What's the two numbers? 0 and what? 40. So it's 40 seconds and 0 seconds. What is my position at 40 seconds? 0. What is my position at 0 seconds? 0. Okay? I don't have to check it. All right, we're all good. It sounded weird, but it's okay. All right, so let's look at the next set of problems. So on our example, what are we doing here? So it's giving me a ball rolling down a slanted driveway, right, guys? Is he rolling up? Oh my God, he's rolling up a slanted driveway. So what it's doing is it's telling us that since it's rolling up, it's going in a positive direction, right? Velocity is 2.5 meters per second. My velocity final is 0 minutes per second at t 5 seconds, right? And I'm looking for acceleration. So I'm doing the same thing as I did before up here with change in velocity over change in time. Does it make sense? You just plug and chug. Only thing that's different with this one is it's giving you positive and negative numbers, correct? Okay, let's look at number 5. A race car forward velocity increases from 4 meters per second to 36 meters per second over a 4.0 second time interval. What is the average acceleration? Now, we know the average acceleration is change in velocity. Do we have 2 velocities here? Okay, what was my velocity final? 36. What's my initial one? 4. What was my change in time? Because it only gave me one time.
So it would be 0 to 4, but.
So it tells us over a 4.0 second time. So I know it's over that period of time. I don't have to subtract it from 0. Mine is meters per second. Yeah, you don't have to ask. So are we ready? So we're going to do alpha y inner. We're going to do 36 minus 4 over 4.0. I got 8. Did everybody get 8? What's my units? We're looking for average acceleration, right? Perfect. Questions? Do you understand where I got my numbers from? Do you understand the math? I'm using it with this formula. Okay, so let's look at number 6. A race car in the previous problem slows from 36 to 15 meters per second over 3 seconds. All right, so my final is what? 15. What's my initial?
36.
What is my time this time?
3 seconds.
Do you see how easy word problems are? Okay, so let's do alpha y inner. 15 minus 36. And I'm going to put it over 3.0. What did y'all get? Negative 7 meters, right? Why is it negative?
Because you're slowing down.
He deaccelerated. Everybody good? Okay, let's go to the next one, number 7. A bus is moving west at 25 meters per second when the driver steps on the brake and brings the bus to a stop in 3 seconds. All right, what's my final velocity? 0. Right? He's come to a complete stop. Subtract, what did we start with?
25.
25 meters per second. All right, what was my change in time? 3 seconds. Okay, now let's do the math. Alpha y inner, 0 minus 25 over 3, which I got negative 8.3 repeating.
Wait, how'd you get a decimal, not a fraction?
I got it right.
I got negative 25 over 3.
Is this the one we're doing?
Oh, was that? Oh, that's seconds. I thought that was a 5.
Oh, no, it's,
That's an S. My bad. I would.
That's
I
the
put
one that-
negative 25 divided by 3.5.
Will you put a decimal on that?
How do you get your to go straight to a decimal?
Sometimes it does and sometimes it doesn't. When it doesn't, it becomes a fraction still. Just put it linear. That means make it straight across.
I have a question.
Sure.
So you said not to put the zero for like the end time. So why do you put the zero for the velocity?
I did just so I could do the formula. Because I could have used a negative 25, right? But I wanted to put the zero here to make sure I understood that was going to be a negative. Because if I didn't, it could be positive, right? Seconds is a positive, never a negative. But velocity can be negative. So I always put the zero.
So the 8.3 is velocity and not time.
8.3 is my acceleration, is what I'm trying to find. That's how fast he's going. And that's meters per second. Make sense? Okay. No, we leave it a different time. No, it's the same time.
Yeah.
Okay, huh? Do you really?
132.
I didn't set my timer right, so that's what he's here for. Let's go ahead and see if we can do the other problem really quick. I got a minute. Okay, so the next one says, what is the average acceleration of the bus while braking? How are we going to figure that out?
This one I was catching on, now I lost it.
What is the average acceleration of the bus while braking?
Half as great. Half as great.
So divided by 2.
Yeah, that's about
So if you divide it by 2, 8.3, what's half of that?
4.5.
Yeah, about 4.15. Perfect.
What is it?
4.15, which is half of what it was. Ain't hard. Okay, so let's go and look at B. If the bus took twice as long to stop, how would the acceleration compare with what you found in part A?
Like, you have to multiply 8.3 and then divide it?
Just be longer. Be longer. That's all we got to do. Okay. Now, want to make sure you understand. So what we did is you did your one pager when you were over here first, right? When we were doing the reading assignment. You've done this. And now when you go over to do the lab, all 3 of these is what you're going to add into your picture.
What picture?
The picture that you're going to submit for today's assignment.
I don't have my laptop.
It's okay. You don't have to have it today.
Okay.
All right, guys in the back. If you would please wipe down your station. Guys in the front, go ahead and go back to the back. You will need your lab paper, your pencil, and you can take your ISM book if you think you might need the math. Okay? Please.